Hello everyone, let's analyze. So today is the day you've been waiting for, the day you've been looking forward to. We know already that every convergent sequence is Cauchy. We've proven that. But is every Cauchy sequence convergent? Well, as you might be able to tell by the theorem right there in front of you, the answer is yes. Every Cauchy sequence is convergent. Of course, if this theorem is true, and I assure you it is. In fact, I'll prove it. Then what we know is, or rather a corollary, is that a sequence is convergent if and only if it is Cauchy. Okay, let's prove the theorem. Every Cauchy sequence is convergent. Suppose AN is a Cauchy sequence. All right. Our goal is to show that it's convergent. What do we mean by that? Our goal is to show that if AN satisfies the definition of Cauchy, it therefore satisfies the definition of convergent. That means we need to find or show that there exists a real number, capital A, so that for any real positive epsilon, there is a natural number n for which the following statement is true. If little n is greater than or equal to big N, then AN minus A in absolute value is less than epsilon. Now we're going to break the proof into two cases. Either the Cauchy sequence assumes an infinite number of values. In other words, the set of values is infinite, or it doesn't. So let's examine each case separately. So let's consider case 1, in which the set of sequence values contains an infinite number of elements. So what do we know? Well, we know that the set is bounded. In fact, you proved it in the first problem of your fourth homework, that every Cauchy sequence is bounded, and this is a Cauchy sequence. So we know it's bounded. We also know, right, by assumption of this case, that it contains an infinite number of elements. Therefore, this set of sequence values satisfies the hypothesis of the Bolzano-Weierstrass theorem, right? The very setting of the Bolzano-Weierstrass, which guarantees us that there is an accumulation point. So let's call it A. Now, notice there is something subtle there. Bolzano-Weierstrass guarantees an accumulation point, but it could be that there's more than one accumulation point. For example, we know that the open interval from 0 to 1 contains an infinite number of values and is bounded, and furthermore contains a lot of accumulation points. In fact, an infinite number of accumulation points. Bolzano-Weierstrass guarantees that you have at least one. Of course, it's important for us to show that a Cauchy sequence set of values has only one accumulation point. Okay, but again, we're guaranteed at least one. Let's call one of the accumulation points A, big A. Our mission is to show that this A is also the limit of the Cauchy sequence, right? So we're assuming it's an accumulation point of the set of values. Now we have to show it's a limit of the sequence. Okay, so we'll start with an arbitrary positive epsilon. Start there. Let epsilon be positive, arbitrary. The fact that A is an accumulation point implies that every neighborhood of A contains an infinite number of values. So certainly the epsilon over 2 neighborhood of A contains infinitely many sequence entries. Now, the fact that the sequence is Cauchy implies there is some natural number n for which the following statement is true. If both little n and little m are greater than or equal to big N, then the absolute value of the difference between an and am here is less than epsilon over 2. And this is true for every index n, little n, and little m that's greater than or equal to this natural number. Now, there's also a natural number k that's greater than n, big N specifically, for which ak is contained in the epsilon over 2 neighborhood of A. Well, how do I know that's true? Well, remember, I know that this neighborhood contains infinitely many points. One of those points has to have an index greater than n. Because if that weren't the case, then that neighborhood would only contain at most n minus 1 entries. If there is no index greater than n contained in this epsilon over 2 neighborhood of A. All right. But of course we know it contains an infinite number. So there's got to be at least one, in fact there's an infinite number of ak values, right, whose indices are greater than n. And let ak just be one of those values. Right? It's in there. It's in the half epsilon neighborhood of A. Okay. So ak is in my half epsilon neighborhood of A, right? In other words, it's a distance of epsilon over 2 from A, right? That is ak minus A, right, is greater than negative epsilon over 2 and less than epsilon over 2. Of course, that comes by just subtracting A from every term, right? We know that the less than or equal to is invariant under addition, right? And subtraction is just adding a additive inverse. And we know from result 2 of our absolute value theorem that this statement is equivalent to this statement. Right? If ak minus A is sandwiched between negative half of epsilon and half of epsilon, then the absolute value is strictly less than half of epsilon. Okay, now we're ready for our big finale. We're ready to put together what we've done to show that we have satisfied our goal claim. Okay? And remember the format of our goal claim. In fact, you might want to write that down and have it in front of you. Right? That's our goal. That's our lodestar, if you will. Let little n be greater than or equal to big N. The same big N as over here and over here. Okay. Then an minus A is equal to an minus A plus 0. Of course, we added 0 in a particular way. We added 0 by adding and subtracting ak. That allows us to employ the triangle inequality to get a less than or equal to, the difference between an and ak and A. Now, this term, right, is less than epsilon over 2. Why is that true? Well, remember, n, little n, is greater than big N, but so is k. K is also greater than big N, right? Then, by the power invested in Cauchy, this is true. Which means, right, since k is bigger than big N, this term is bounded above by epsilon over 2. It's less than epsilon over 2. And of course, this term here, right, from right above us, also less than epsilon over 2. And half an epsilon plus half an epsilon is a full entire epsilon. Okay, we have just shown that our goal statement 1 is true. So we've proven our result for this case, right? Remember, the particular case where my Cauchy sequence assumes an infinite number of values. Okay. Now, you might be concerned about, wait a second, how do we know there are not other accumulation points? Well, we just showed that the accumulation point A is a limit, and limits are unique, like snowflakes. In fact, it was the subject of one of our previous lectures. So there is no other limit. And if there's no other limit, there's no other accumulation point. Because in fact, every neighborhood of A contains all but a finite number of sequence entries. So there can be no other limit. Alright, now let's go to case 2, right? Which is the case where our sequence assumes only a finite number of values. Now, if our sequence assumes a finite number of values, then the set of values is bounded but finite, right? Bounded but finite, which means Bolzano-Weierstrass has nothing to say. He has nothing to say. He has no power here. However, if the set contains, let's say, L values, right? Well, L is some finite integer, then we can list the values, right? So remember, this here, right, highlighted, that's the set of all values that my Cauchy sequence assumes. And these are all the different values. So alpha 1, alpha 2 through alpha L, right, are all different numbers, okay? And every entry in my Cauchy sequence is one of those L numbers. Well, Cauchy sequences is a statement about the difference between two elements. Well, if each element can only be one of L different entries, right? If I were to take the difference between every possible entry, there's only L times L minus 1 possible positive differences. In other words, for each j not equal to k, right, for j and k both being integers 1 through L, the difference between alpha j and alpha k is, in absolute value, positive, right? More importantly, not 0, because if it was 0, they'd be equal. Okay? And these difference values, there's only a finite number of them, right? In fact, we can say exactly how many there are. There are L times L minus 1. So since there's a finite number of differences, the set of all possible differences has a minimum. Let's call that minimum D. Okay? D is the smallest difference between alpha j and alpha k for j and k not equal to each other. Of course, j and k must be integers 1 through L. Now remember that our Cauchy sequence, the sequence of values an, right, is Cauchy, which implies there exists a natural number, capital N, for which this statement here is true. If little n and little m are greater than or equal to big N, then the absolute value of the difference, an minus am, is less than half of D, where D is the smallest difference. Essentially, d over 2 is taking the place of epsilon in our Cauchy definition. And we can do that because epsilon in the Cauchy definition is arbitrary. And certainly d is positive and d over 2 is positive. So it can play the role of my arbitrary epsilon. But it's not possible for there to be a difference of values less than d over 2 unless that difference is 0. Right? Because the smallest non-zero difference is d. So if the difference is less than the smallest possible non-zero difference, the only remaining possible difference is d. That means every sequence entry after big N is equal, entirely the same, because the difference is less than the smallest possible non-zero difference, which means it's 0. So what we have is a sequence that at some point, specifically the point big N, the sequence becomes constant. Now, you proved in problem 4 of the third homework that such a sequence is convergent. And every convergent sequence is Cauchy. So therefore, in the finite number of possible values, a Cauchy sequence is also convergent. QED. When I took real analysis as a graduate student, we would get together in groups and go through the homework. Now QED stands for something in Latin. I don't know what. I don't remember. My Latin is rusty. But there is a member of our group, Shakia. She said QED stands for quit, everything's done. I like that. Now remember the corollary. A sequence is Cauchy if and only if it is convergent. In other words, Cauchiness implies convergentness, and convergentness implies Cauchiness. They're equivalent, they're one and the same. Now a quick note, this equivalence sometimes is referred to as the completeness or Cauchy completeness of the real numbers. What is meant by that? Well, if you remember the axioms that we adopted to build the real numbers, right? First we had a field and we said, no, that's not enough, because we could have a 2-element field or a 4-element field. And then we said, okay, well, what about an ordered field? And we said, no, that's not enough, because the rationals are an ordered field, and how would we get irrationals? So we completed, you can't see me making air quotes, but I'm doing it right now. I'm making air quotes. We completed the real line by adding the axiom of the least upper bound property. That is, every non-empty set on the real line that is bounded from above has a least upper bound. Well, another way of completing the real line is to say a real line is an ordered field that also contains the limit of every Cauchy sequence. That would mean irrationals, all of them, can be expressed as the limit of a Cauchy sequence or a convergent sequence. And if we think back to the very first day when we pondered the existence of the square root of 2, our inclination was, well, let's approximate it, and let's improve the approximation by getting closer and closer. In fact, we applied a bisection algorithm, right? We said 1 is not enough and 2 is too much. Goldilocks says pick 1.5. Nope, that's too much. Try 1.25. That's too little. Try halfway between 1.25 and 1.5. And if we carried on this procedure, we would have ourselves a Cauchy sequence that converges to the square root of 2. The square root of 2 is the limit of a sequence of rational numbers. And in fact, every irrational number can be expressed as the limit of a convergent, or equivalently a Cauchy sequence. That's it for today.